Okay, so this is the second video in session 2 of our Pre-Leaving Cert Algebra revision course. In the first video we took a look at solving linear equations, and today we're going to concentrate on solving linear inequalities. And it makes sense to do one after the other, as inequalities are very closely linked to equations, and a lot of the rules that we picked up in solving equations can be applied to solving linear inequalities. It's not a very big topic on the Leaving Cert higher level paper. Having looked for some trickier examples that we could try later on, there's very few examples in the past papers, even parts of questions where linear inequalities turn up, and we're much more concentrated at Leaving Cert level with quadratic inequalities and inequalities of other types. Having said that, it's important to kind of look over it as, you know, the basis for the signs is important when you go forward to do those quadratic inequalities. And there is cases where we may see an inequality on a Leaving Cert higher level paper, and certainly on a Leaving Cert ordinary level paper. So as before, we're going to run through 10 basic examples, each one slightly different before and increasing in difficulty level. We look at some trickier examples, mostly taken from the Junior Cert higher level course. And you know, one example where I've adapted it from the Leaving Cert higher level, and then of course there's the big bank of past questions that people can practice if they're still having difficulty. Okay, so before we look at the 10 basic examples, we're going to briefly go over the inequalities themselves. We're going to talk about the signs and their directions and what they mean. We'll talk about the different types of number and the symbols used for those. And then we'll also briefly discuss the number line, in particular in the context of giving a solution to an inequality and graphing it on a number line. So the first thing to look at is, in the last question we were interested in solving equations. And when we're interested in solving equations, we have an equal sign, which we're very familiar with. And the very last line of our sum will be something like x equals 4. Telling us that x takes the value of 4 in the context of the question that we're doing. And in linear equations, there's one and only one solution, and we saw that in the last examples. What we're looking at now is we want to take a look at these 4 inequalities. So these signs we learned in primary school, and we're just going to refresh them now. We would have also seen them obviously in our Junior Cert. So the first one we're going to look at is that sign there, which reading from left to right means less than. And so I can make a very simple statement. I could say that 4 is less than 7, and that's true. If we're solving an inequalities question, we're not trying to get down to something like x equals 4. We're trying to get down to something like x is less than 4, which means that x takes a whole range of values. X isn't just one particular number. X could be any number that's less than 4. And so the number 3 is less than 4, that's a solution. The number 2 is less than 4, that's a solution. Depending on the number types we used, minus 10 is less than 4, and that would be a solution. So in inequalities, there's not just one solution, there's a range of solutions. The next sign is the backwards version of the one we've just written, and that obviously means greater than, and to make a simple statement here, we could say that 10 is greater than 5. And again, we'll solve an inequality, and maybe at the end of an inequality we might get that our variable, let's say y in this case, is greater than 11, which means that y is every value that's bigger than 11. So it's the value 12, it's 20, it's 33. Any number that's bigger than 11 would be a valid solution for our question. The last two symbols are just extensions of the two we've written up already. So this is less than, and if you draw a line underneath it, it just means less than or equal to. So if I put up, for example, x is less than or equal to 7, that means that x is every value that's less than 7, but it could also be equal to 7. So it's going to be 6 and 5 and 4 and 3. You can take any of those values, but it can also equal the number 7. So 7 is a possible solution too. Finally, we have the reverse. So just drawing the greater than sign and then the line underneath it. Obviously, that just means greater than or equal to, And the same applies. So if I have a solution that says y is greater than or equal to 2, y is every number that's bigger than 2, so 3, 4, 5, 6 as far as infinity, but also is equal to the value 2 as well. Okay, so that's a quick run through each of the signs. And what we're going to do now is just take a look at the types of number that could be included in the question. And what do I mean by that? So we're going to look at this inequality in 3 different ways. So here's an inequality that says x is less than 4. And so I could say to you, well, x is the value 3, it's the value 2, it's the value 1. But depending on what type of number has been included in the question, there may be more or less solutions. And what do I mean by that? Well, first of all, if we have a look at this n symbol, n stands for the natural numbers. And the natural numbers are the positive whole numbers. So starting at 1 and then continuing on with all the positive whole numbers, we have 1, 2, 3, 4, 5, and that goes as far as infinity. So if you're given a question and then after your inequality, you're given instructions as to what sort of number system we have to stick to. So for example, x is an element of n. That means when we're given our solution, we can only list positive whole numbers. So we've done an inequality. We've ended with this line. This is the last line of our inequality. X is less than 4. And I've been asked to put it on a number line. So what is the solution? It's all the positive whole numbers less than 4. So 3, 2, and 1. And we don't count 0 as a natural number. So it's only the positive whole numbers. So if I'm putting it on a number line, I color in these dots here. So I have dots to represent that it only takes the value of the whole numbers here, 1, 2, and 3. It doesn't include decimals or fractions that lie between those numbers. Okay, looking at the exact same example, but just with a different number system. Let's say we had x is less than 4, but this time we are in the integers number system. So they want only solutions that are integers. So z stands for the integers. What are the integers? The integers are all the positive and negative whole numbers, and they also include 0 as well. So starting at minus infinity, and then all the negative whole numbers as far as 0. So we come along and we get minus 3, minus 2, minus 1, 0, and then we have all the positive numbers, 1, 2, 3, 4, etc., as far as plus infinity. Again, we're not including any fractions or decimals. They're only positive and negative whole numbers, and again, including 0. So x less than 4 this time is obviously again going to be 3 is less than 4, 2 is less than 4, 1 is less than 4, but 0 is also less than 4, and minus 1 is, and minus 2 is, and every number as far as infinity. We're not going to be able to color in every single dot, so what we do instead is, at some stage on one of the dots that we've colored in, we put an arrow that just points to the left that says these dots would continue to be colored all the way to minus infinity. So minus 100 would be a valid solution, minus 1000 is also a valid solution. So any number less than 4 would be a solution to this equation. Okay, the final type of number that we're going to look at in this is going to be the real numbers. And so real numbers are obviously all the positive and negative whole numbers, but they also include all the fractions and decimals that lie in between. So if I have the final line of a sum that says x is less than 4, and in the sum I've been given the instruction that x is a real number, well, it also includes things like 2.5. It includes numbers like minus 1.3. It includes fractions like a half. And so to include all of these things, I have to shade in the number line. And again, I put an arrow at some stage at the end of the number line to say it also includes all the numbers less than 4 as far as minus infinity. One key important point is if x is less than 4, it means it's not equal to 4. And so what we do is we have a hollow dot on the 4. So a hollow dot representing that 4 is not included, but all the numbers immediately before 4 and going on forever to minus infinity would be included in the solution. If we had x is less than or equal to 4, well, in that case we would color in that dot and make it a full dot. A full dot represents that it's also equal to the number. Okay, so if we're given a number line, we have to take consideration of whether it's a natural number, integers, or a real number. Natural numbers and integers, remember, will be colored in with full dots. And then if we have a real number line, we have full dots to represent if a number is included, and we have shading in to represent all the numbers in between. And then obviously hollow dots will represent that it's not included. Okay, so let's have a look at our first basic example. So this example says, find the values of x for which 3x minus 2 is less than 10. So let's write our sum up here on the left hand side. 3x minus 2 is less than 10. Now we take note that the solutions are natural numbers, and we'll discuss that in the very last line of our sum after we've got our final line of our inequality. The key thing with inequalities are that we use the same rules as we used for equations. So we're trying to collect the x terms on the left hand side and the number terms on the right hand side. So I'm going to proceed in this question as if it was an equation, collecting x's on the left and numbers on the right. So there's one important difference between equations and inequalities, and that's when we divide by negative numbers, and we'll discuss that in one of the examples coming up. So treating this as if it were an equation, what we do is I'm going to keep the x's on the left hand side, which means that 3x is already on the left. I'm just going to keep it there. I'd like to remove a minus 2 from the left hand side, which means adding a 2 to both sides. If I add it to the left hand side, it'll get rid of the 2, and then that means obviously I'm adding a 2 to the right hand side, and 10 is a number, it's already on the right hand side. Simplifying the right hand side now, I get 3x is less than 12. And then as we would do in an equation, we want to get rid of the number beside the x, and so we're going to divide both sides by that number. And if I divide both sides by 3, 3x divided by 3 is 1x, and then we get 12 divided by 3 on the other side. And some people might skip writing 12 over 3 and just straight away write down the number 4. That's fine. I'm just going to do it on the next line so we can see the step that I took. So x is less than 4 is the solution to our question. We need to go back and read the question carefully. So it says find the values of x. So they actually want us to list all the values, list the solution here. So when I go to list the solution, I want to list all of the natural numbers that are less than 4. And so what are the natural numbers that are less than 4? Well, we have the number 1, 2, and 3. They're the only natural numbers less than 4. We can see there's no equals in this question, so it's not equal to the number 4. And we don't include any negative numbers. The number minus 3 is less than 4, but why is it not a solution to this question? It's not a solution to this question because we were given the instruction that we could only have natural numbers. The question doesn't ask me to do a number line, so you don't always have to do a number line if you're not asked for one, but just to draw one so we can see what it might look like. We'll start at 0. There's no need for negative numbers because this is a natural numbers question. I'll skip every 2 spaces just to have the units. So it's 1, 2, 3, 4, 5. It's up to you how far you want to go. There's no need to go much beyond 3 because 3 is the first solution in our question working right to left. So I'll just put down 6. And now to put 1, 2, and 3 on the number line, well, it's a natural number line, which means we colour in full dots like this. So we don't shade in between them because it's not including any of the decimals or the fractions that lie between, let's say, the numbers 2 and 3. So when we did equations, there was only one solution that would satisfy the original equation. We found an answer, and if we were asked to verify it, we could sub it back in, and we checked that that was indeed the one solution to the question. So in this inequalities question, we have 3 values of x that satisfy this equation, and let's just go and check them. So if we write down the equation again, 3x minus 2 is less than 10, and let's just check that x equal to 1 was a solution of this equation. So we put in 1 for the x, so 3 times 1 minus 2 is less than 10. 3 times 1 is 3, minus 2 is less than 10, and then 3 minus 2 is obviously 1, and 1 is indeed less than 10, and it shows that 1 was a solution to this equation. Similarly, if I tried 2 or 3, we'd equally get valid solutions to the equation. Let's try a number that wouldn't be a solution to this equation. So we're going to pick a number that's not less than 4. So for example, let's pick the number 5. So let's sub 5 into the original equation and show that it's not a valid solution to the inequality. So 3 times 5 minus 2 less than 10. 3 times 5 is 15, minus 2 is less than 10. And then 15 minus 2 is 13, and 13 is not less than 10. And so we can see that 5 was not a valid solution to this equation. So what are the valid solutions? 3, 2, and 1. One final point. Obviously, a number like 1.5, which lies between 1 and 2, that would be normally a valid solution to this equation had we not been given the instruction that x has to be a natural number. We're only looking for natural number solutions to the question. Okay, so example 2 then asks us to solve the inequality 3x minus 7 is greater than or equal to minus 4. So we just put a minus on the other side just to make it a little bit different for example 2. Again, we are interested in natural number solutions, and when we go to put these on the number line, we just have to make sure that the solution is only represented by natural numbers. So like an equation, we're going to keep the x terms on the left hand side and bring the number terms to the right hand side. So 3x is already on the left hand side. To get rid of minus 7 from the left hand side, I have to add a 7 to both sides, which means that on the right hand side I now have minus 4, which was already there, plus the 7. Tidying up the right hand side, I have 3x on the left is greater than or equal to plus 3. 7 minus 4 is plus 3. And then I'm going to divide both sides by 3 to get the x on its own. So 3x divided by 3 is 1x, and 3 divided by 3, I'll just write it like that first, and then x is greater than or equal to 3 divided by 3 is 1. And again, a lot of people will skip this line. The reason sometimes I don't skip that line and I write 3 over 3 is, remember in linear equations we were left with lots of fractions, and we'll see later on in the examples here as well that we'll have fractions on this side, and so it's important to know what happened to 3 here. We divided both sides by 3, which meant that the number on the right hand side gets divided by the number that was beside the x, or the number that we're looking for. Okay, so x greater than or equal to 1 is the solution set to this equation. And to put that on a number line, again, we're interested in natural numbers. It's greater than or equal to 1. In this example, we have an equals to 1 also. And so the first dot that I'm going to color in is 1. So x is equal to 1. And now it's every natural number greater than that. So it's going to be 2 and 3 and 4, etc. Now, it's up to us to decide kind of where to stop. Obviously, we can't color in every dot as far as infinity. So at some stage then we just put an arrow on one of the dots to say that, look, this includes every natural number going forward as far as infinity. X is greater or equal to 1. You might say to me that the number 2.5 is greater than 1, which it is. Why is it not a solution? It's not a solution because we're only interested in natural number solutions. So example 3 is a key example in demonstrating the difference between the rules we would have learned for solving equations and the rules we use for solving inequalities. And that key difference is when we divide or multiply by negative numbers. So let's write it down first of all, and then we'll discuss what we mean by that. So 6 minus 3x is less than or equal to 15. So we're looking for a solution set to this inequality. What I'm going to write down here on the right hand side is just a general rule of thumb that I use. You don't have to do this, and we'll do this question in 2 ways, but the general rule of thumb that I use is I like to bring the x's, like we want to collect the x's on the left or the right. Generally it's the left hand side, but it doesn't have to be. So the rule of thumb I would use is to collect the x's on the side where they will be positive. So at the minute we can see that we have a negative 3x or a minus 3x on the left, and so what I would like to do is I would like to collect the x's on the right hand side, because if I collect them on the right hand side I'll have positive value for the x's. Now, like I said, we're going to do it in both ways, so you don't necessarily have to do it like that, but we'll see in a second why it's a useful way to do it. So I'm going to collect the numbers on the left hand side. So 6 is already on the left hand side, and then 15 is on the right hand side. To get rid of it from the right hand side I have to subtract 15 from both sides, which means putting a minus 15 on the left hand side. I have a minus 3x on the left hand side, which I'd like to get rid of from the left, so I'm going to add a 3x to both sides, which means that on the right hand side I need to add a 3x. So 6 minus 15 is minus 9, and that's less than or equal to 3x. As before, I'm trying to get the x on its own, so I'm going to divide both sides by the number beside the x, which is 3. So minus 9 over 3 is less than or equal to x. And then finally, tidying up minus 9 divided by 3. Minus 9 divided by 3 is minus 3. And minus 3 is less than or equal to x. Or another way of saying that is that x is every number bigger than or greater than or equal to minus 3. Now, why did I do it that way? Well, I did it that way because here I was able to divide by a positive 3. And the rules in inequalities are that if you divide by a positive number, the sign, the inequality can stay the same. You don't have to turn it around. If you divide by a negative number, then you have to change the direction of the inequality. So let's show you what I mean by that. So let's just make a bit of space here. We'll just pull this over. Okay, so we're going to do the same sum again, just beside it. So let's have a look. So let's write it down again. 6 minus 3x less than or equal to 15. Now, this time I will keep the x's on the left-hand side, as we would normally do with an equation. So I'm going to keep minus 3x on the left-hand side, and then 15 is the number on the right-hand side, and I want to put all the numbers on the right-hand side, so that means remove a 6 from the left-hand side by subtracting a 6 from both sides. Here I get that minus 3x is less than or equal to, now 15 minus 6 is plus 9. Now, here I want to divide by minus 3. To get the x on its own, I need to divide both sides by the number beside the x, which is minus 3. So I'm going to do 9 divided by minus 3. And this is the key difference in an inequalities question. If you divide by a negative number, you need to change the direction of the inequality. So that's the key rule that we have to learn in example 3. And going forward, if we ever decide to divide by a minus number to get the x on its own, we have to remember to change the direction of the inequality. So finishing off the sum, then we have x is greater than or equal to 9 divided by minus 3. A plus divided by a minus is a minus, and 9 divided by minus 3 then becomes minus 3. So we have a final solution of x is greater than or equal to minus 3, which is the same as we had on the left-hand side here. We just read it backwards. So I like to use this rule of thumb where I bring the x's to the side where I know they're going to be positive, and that way I never have to worry about changing the direction of the inequality. Now you might wonder why this rule works, and let's just have a look at why we can't divide by a negative number. So we'll just do a quick example. So let's say I said to you that minus 8 is less than 6, which it is. And then I decided for some reason to divide both sides by minus 2. So if I divide minus 8 by minus 2 and 6 by minus 2, that's fine. We're doing the same thing to both sides. Minus 8 divided by minus 2 is the number 4. And 6 divided by minus 2 is minus 3. Now, if I keep the sign as it was, well, 4 is not less than minus 3. And so now my sum is incorrect because the rule is when you divide by a negative number, it changes the sign of the inequality. So I've divided by a negative number here. I've divided both sides by minus 2. And so what I have to do is if I change the direction of the inequality, now it's true. 4 is bigger than minus 3. So it just shows the importance, and when we're multiplying across the sum or dividing across the sum by a negative number, we have to make sure just to change that sign in the middle. So another rule of thumb I like to use is when we have a number line that has no numbers on it already, use the solution to the question as the middle of your number line. So I'm going to put minus 3 in the middle of my number line. And then that gives me space to put some numbers either side to demonstrate the solution. So on the right hand side, I'm going to put minus 2, minus 1, 0, and so it continues on for infinity in that direction. And then to the left hand side I have minus 4, minus 5, minus 6, and it continues on infinity in that direction. First of all, I'm going to take a look and see is x equal to minus 3, and it is. So I'm going to put a full dot on the number minus 3. Minus 3 is a solution and we have to colour it in. Then we look again at the solution. It says x is greater than or equal to minus 3. So not only is it equal to minus 3, it's every number bigger than minus 3. And because that includes the fractions and the decimals in between the whole numbers, we shade in the number line. And then at some point along that shaded line, we put an arrow to denote that that's going to be shaded in forever as far as plus infinity. So the solution set to this equation is every number that's bigger than or equal to -3, including all the fractions and decimals. So example 4 gives us another chance to look at this idea of collecting the x terms on the side where they'll be positive. So minus x plus 6 is greater than 3x minus 9. So I'm going to collect the x terms on the right hand side and the number terms on the left hand side. So on the left hand side I have a 6, and then to remove the minus 9 from the right hand side I'm going to add a 9 to both sides. So on the left hand side I have 6 plus 9. That's greater than 3x is already on the right hand side. And so to remove the minus x from the left hand side, I'm going to add an x to both sides. 6 plus 9 is equal to 15, and that's greater than 3x plus x is 4x. I'm going to divide both sides by the number beside the x, which is 4. So 4x divided by 4 is x, and 15 divided by 4 is 15 over 4. Now 4 doesn't actually go into 15, and when we're putting the number on a number line, it is a good idea to turn it into a mixed number. So 4 into 15 goes 3 times and 3 remainder. So 15 over 4 is equivalent to 3 3/4. Now let's have a look at if we had kept the x's on the left hand side, just to show that the approach works in either way. You'll get the same answer either time, but again, we just don't have to worry about changing the direction of the inequality if we divide by positive numbers. So doing the sum again, let's write it out. Minus 6 plus 6 is greater than 3x minus 9. So collecting the x terms on the left, minus x is already on the left hand side. To remove a 3x from the right hand side, we have to subtract a 3x from both sides, and that's going to be greater than minus 9 is already on the right hand side. And to get rid of a plus 6 from the left hand side, I'm going to subtract a 6 from both sides. Minus x minus 3x is minus 4x, and that's greater than minus 9 minus 6 is minus 15. Now, I need to divide both sides by minus 4 if I'm going to isolate the x and get the x on its own. So minus 4x divided by minus 4 is 1x, and then we have to divide the right hand side by minus 4. So minus 15 over minus 4. Now because I've divided by a negative number, the rule is that I have to change the direction of the inequality. So x is less than minus 15 over minus 4, but we know that a minus divided by a minus is a plus, and so x is less than 15 over 4, which is essentially the same as what we had over here on this side. Here it read backwards. We have x is less than 15 over 4, or 15 over 4 is bigger than x. And this reads the same way. It says x is less than 15 over 4. And again, 15 over 4 is the mixed number 3 3/4. So what kind of a number line is this? Well, it's a natural number line. So we start at 0, and then I'm just going to put in 1, 2, 3, 4, 5, and that should be enough. Now, x is every number that's less than 3 3/4. So obviously 4 is not included. 4 is bigger than 3 3/4. We don't include 3 3/4, which would be roughly here on the number line, because it's not a whole positive number. So the first natural number less than 3 3/4 is the number 3. And then we're going to colour in every natural number, whole positive number, less than that. So we have 1, 2 and 3 is the solution of the equation. So that's it written on a number line. The question though says to list the solutions. So we're using the number line just to demonstrate how it might look on a number line in case that was the question. But this question just wanted us to list the solution. So I'll just put them in a pair of brackets, and the solution is 1, 2 and 3. They're the values that satisfy this inequality. So in example 5, we have that 2 on 3x minus 2 plus 5x is less than 30. So first thing I'm going to do is I'm going to multiply out the brackets to remove those. So 2 by 3x is 6x, 2 times minus 2 is minus 4, plus the 5x, and that's less than 30. I'm going to collect the x terms on the left hand side, so I have 6x plus 5x already on the left. And I'm going to collect the number terms on the right hand side. So 30 is on the right hand side, and to remove the minus 4 from the left hand side, I'm going to add a 4 to both sides. 6x plus 5x is 11x, and that's going to be less than 30 plus 4 is 34. Now note here that 11 doesn't go in evenly into 34, so I want to divide both sides by the number next to the x, which is 11, and so I'm just going to have to put the 34 over 11, just knowing that it doesn't divide in evenly and give me a whole number. So we want to write this as a mixed number just so we can write down the list of the solutions. So 34 over 11, 11 goes into 34 3 times with 1 remainder. So 34 over 11 is the same as 3 and 1/11. So the question says to list the solutions, and we're looking for only natural number solutions that are less than 3 and 1/11. And so listing the solutions, the natural numbers that are less than 3 and 11 are 1, 2, and 3. And there's no need for a number line if they don't ask us for one. Question 6 adds to the difficulty just by adding in some fractions into the question. So we have an inequality 2 minus 7/8 x, and that's less than 1/4. Again, I'd like to collect the x's on the side where they'll be positive. So I'm going to collect the x's on the right hand side and the numbers on the left hand side. So 2 is already on the left hand side, and to get rid of the quarter from the right hand side, I'm going to subtract a quarter from both sides. On the right hand side then, I want the x's, and so I need to remove the minus 7/8 x from the left hand side, which means adding 7/8 x to the right hand side. 2 minus a quarter, I could probably do that in my head, but what I'm going to do is I'm going to just turn both of them into numbers over 4. So 2 is the number 8 over 4, minus obviously a quarter is already over 4, and that's going to be less than 7/8 x. 8 over 4 minus 1 over 4 is 7 over 4, and that's less than 7/8 x. So I'm going to divide both sides by 7/8, so I get on the left hand side 7 over 4 divided by 7 over 8, and that's less than x. And then we can come over to the side of the page to do a quick calculation of what 7 over 4 divided by 7 over 8 would be. Remember, when we're dividing fractions, we can invert or turn upside down the second fraction and multiply it. So 7 over 4 times 8 over 7 would be the same thing. 7 times 8 is 56, and 4 by 7 is 28. And so 7 over 4 times 8 over 7 is actually the number 2. And so our solution is that x is greater than 2. It is okay to put any of this work into the calculator, like this step here where we're dividing these fractions. We can put them into the calculator, but I always recommend where there's an opportunity to do fractions, to go ahead and do those, so that when you have variables in the fractions, the rules will come more easily to you. Okay, so it asks us to put it on a number line, so it's a real number line. As I mentioned before, I like to put the solution that I found in the middle of the number line, so 2, and then put a couple of numbers either side of that just to demonstrate the solution more clearly. So we go from -1 to 5 on the number line that I have. So x is greater than 2. Note that it's a real number line, so we're including all the fractions and the decimals, but it's not equal to 2. 2 is not a solution to this equation. So I'm going to put a hollow dot there where the 2 is. What I want to do now is I want to color in or shade all of the numbers, fractions, decimals, everything that comes after 2. X is greater than 2, and so what we do is we color in the number line, and then at some point what we do is we put an arrow at the end just to demonstrate that it's going to be every number, decimal, fraction, and whatever it might be, bigger than 2 as far as infinity. Okay, so in question 7 we're asked to solve 2 inequalities, and then there's a third part asking you to link the 2 previous parts. So let's have a look at this. So question 1, first of all, asks us to solve 4x minus 3, do you get me pen? 4x minus 3 greater than or equal to 1. So a fairly simple linear inequality. So first of all, I'm going to collect the x terms on the left hand side, so 4x can stay on the left, and then I'm going to collect the number terms on the right hand side. 1 is already on the right hand side. To remove the minus 3 from the left hand side, we add it to both sides. So 4x is greater than or equal to 1 plus 3. That means that 4x is greater than or equal to 4. We're going to divide both sides by 4, and we get x is greater than or equal to 4 divided by 4, and so x is greater than or equal to 1. So fairly straightforward. The second part should be straightforward too, so let's have a look at that. We are going to solve the inequality 4 minus 3x is greater than or equal to minus 5. So we can keep the x's on the left, in which case we'll have a negative number in front of the x, minus 3. And when we divide by that minus, we're going to have to change the direction of the inequality. Or we can just decide to bring the x's to the right hand side, which is what I'm going to do. So the numbers are going to be on the left. We have 4 already on the left. Minus 5 to get rid of it from the right hand side. We're going to add it to both sides. And that's greater than or equal to get rid of the minus 3x from the left hand side, I'm going to add a 3x to both sides. 4 plus 5 is 9, which is greater than or equal to 3x. I'm going to divide both sides by 3, the number beside the x, to get the x on its own. So x would be less than or equal to 9 over 3. And then finally x would be less than or equal to 3. Now you can see there I'm reading from right to left just because my x is on the right, and so it says x is less than or equal to 3. 3 is greater than or equal to x. Okay, the third part of the question then asks us to combine the two. So in part 1 we have a set of numbers that's bigger than or equal to 1, and in part 2 we have a set of numbers that's smaller than or equal to 3. And so the third part asks us to write down the whole numbers that satisfy both equations. So in words, we're looking for numbers that are bigger than or equal to 1 and smaller than or equal to 3. Now there's a way we can write this nicely. It's called a double inequality. So what we're going to do is we're going to put the x in the middle, and we know that x is bigger than or equal to 1 but smaller than or equal to 3. And this notation here is extremely important going into Leaving Cert, because when we do what's called quadratic inequalities, quite often the solution is in this form. So any number that's bigger than or equal to 1 or less than or equal to 3 satisfies both inequalities. And so finally, just writing down the whole numbers which satisfy this, we have 1, 2, and 3. They're the whole numbers that are bigger than or equal to 1 but smaller than or equal to 3. And again, this double inequality notation is something that's going to be important for you to carry through to the Leaving Cert cycle. Okay, so example 8 is along similar lines, so we'll just make space for the 3 parts of the question. And what we're going to do is we're going to solve the 2 linear inequalities first, and then we'll combine the answers somehow in the third part. So the first part asks us to solve the inequality 6x minus 8 is less than or equal to 4. I'm going to collect the x's on the left, so 6x on the left, and the numbers on the right hand side. 4 is already on the right. To get rid of the minus 8 from the left hand side, we add 8 to both sides. 6x then is less than or equal to 12. I'm going to divide both sides by 6, giving me x is less than or equal to 12 over 6, and x is less than or equal to the number 2. So fairly straightforward linear inequality. The next one is a little bit more tricky in terms of the fraction that's involved. So we have 1 minus 3x over 5 is less than 2. In a linear inequality like this, or linear equation, if we have a fraction on one side and we have a number on the bottom and we would like to get rid of that fraction, the handiest thing to do is to multiply the whole sum by 5. So what we're going to do is we're going to multiply the left hand side by 5, which will remove the 5 from the bottom of the fraction, and then we're going to multiply the right hand side by 5, remembering that whatever we do to one side we have to do to the other side. So multiplying the left hand side by 5, I'm left with 1 minus 3x, and then multiplying the right hand side by 5, I'm left with 2 by 5, which is 10. Some people see a shortcut of just multiplying up the 5 onto the other side. So 5 by 2 is 10. And that's an okay way to think about it, but remember what we're really doing is multiplying both sides by 5, which gets rid of the 5 from the denominator of the fraction, and then multiplies the right hand side by 5. One further thing, if we were multiplying across by a minus number, remember we would have to change the direction of the inequality. Multiplying and dividing by negative numbers change the direction of the inequality. Okay, so I'm going to collect the x's on the right hand side because I'd like them to be positive, and if I collect them on the right hand side, that minus 3x will be a plus 3x. So the numbers are going to be collected on the left. So we have 1, and then to get rid of 10 on the right hand side, we're going to subtract a 10 from both sides. To get rid of the minus 3x from the left hand side, I'm going to add a 3x to both sides. 1 minus 10 is minus 9, which is less than 3x. And then I'm going to divide both sides by the number beside the x, which is 3. So I have x is greater than minus 9 divided by 3. So x is greater than minus 3. So in part 1 of the question, the set A, and we'll just get a different color pen for this. So set A is all of the numbers less than or equal to 2, and then set B is all of the numbers that are bigger than minus 3. The third part of the question asks us to find A intersection B, and all they're asking here is what's common to both sets. So what numbers are included in set A and set B, and in words, what are the numbers that are bigger than minus 3, so the numbers that are bigger than minus 3, but less than or equal to 2. And here we have our double inequality, just the notation we can use to say that x is numbers that are bigger than minus 3 but less than or equal to 2. And this is the set A intersection B, the set of elements that are common to both. So we're using language that we would have used for our junior cert from sets, so set notation and elements and intersection. But basically in words, all we're saying is what are the numbers that are bigger than minus 3 and less than or equal to 2. Now again, it asks us to list them, and we can see that this question is integers, so we can list positive and negative whole numbers. So I'll do my double set of brackets. X is bigger than minus 3, so we can't list minus 3 in the solution. It's not equal to minus 3. So the first number bigger than minus 3 is minus 2. Then we have minus 1, we have 0, we have 1, and then we can include 2 because there's an equal on that inequality. So that's the solution set of A intersection B, elements that are common to part 1 of the question and part 2 of the question. So we're going to have a look at compound inequalities. Now, this is a topic that was removed from the Junior Cert higher level course from 2019 going forwards, and it wasn't a question that was popular at Leaving Cert level either. So it's something that we're looking at for exploration purposes, just to look at the idea of a double inequality once again. The difference between this one and ones we've seen previously with the x in the middle is that this one hasn't been solved out. So we don't know what the solution to this inequality is, whereas when we have the x on its own in the middle, we have a set of solution values for x. So there's a couple of methods to doing this question. I'm going to show you the preferred method I use first, and then we'll have a look at a different method. So minus 4 is less than or equal to 3x minus 1 is less than 8. And again, what we're looking for is values that we could sub in for the x here, so that when we do, this middle part of the inequality would be a number that's bigger than or equal to minus 4 and less than 8. So what I'm going to do is I'm going to split this sum into two separate linear inequalities. So the first one is going to be minus 4 is less than or equal to 3x minus 1. And then I'm going to do a separate inequality that looks at 3x minus 1 less than 8. We'll just write it down here. Okay, so I have two separate linear inequalities, and I'll just do them one at a time. So starting with the one on the left, I have the number terms I'm going to collect on the left hand side. So I have minus 4 already on the left, and then to get rid of the minus 1 on the right hand side of the inequality, I'm going to add a 1 to both sides. So minus 4 plus 1 is less than or equal to 3x. The next thing I'm going to do is I'm going to tidy up the left. Minus 4 plus 1 is minus 3, which is less than or equal to 3x. And then I'm going to divide both sides by 3 to get x is greater than or equal to minus 3 divided by 3 is minus 1. So we have part of the solution. X is the values that are bigger than or equal to minus 1. But we also have this condition on the right hand side. So keeping the x's on the left, first of all, I have 3x. And bringing the numbers to the right hand side, I have an 8 on the right hand side. And then what I'm going to do is I'm going to add a 1 to both sides to get rid of the minus 1 on the left. 3x then is less than 9. And if I divide both sides by 3, I get x is less than 3. And this is the second part of my solution. So x is any number that's bigger than or equal to minus 1, but less than 3. And we can make a double inequality out of this just to represent that. So minus 1 is less than or equal to x, which is less than 3. The question asks us to list these elements. So we're going to list all of the integers, the positive and negative whole numbers, that are bigger than or equal to minus 1, but less than 3. So the first one obviously is minus 1, as it's equal to minus 1. And then we have 0, 1, 2, and we don't count 3 because we don't have an equals less the inequality on the right hand side. So we close off our brackets, and that's our solution set. Okay, so let's have a look at an alternate method of doing this problem. So what we're going to do is we're going to write down the inequality once again. So minus 4 is less than or equal to 3x minus 1, which is less than 8. And I'm going to try and work with the three sections of this sum. The first section, which is on the left of the first inequality, the middle section, and then the section at the end, which is on the right hand side of the latter inequality. What I'm going to do is I want to get down to a situation where I just have the x on its own in the middle of this double inequality, similar to my final solution down here on the left hand side of the first version. So how am I going to do that? Well, to reduce the 3x minus 1 down to an x, I'm first going to get rid of this minus 1. Now to get rid of a minus 1, I'm going to add a 1 to each of the three sections. So I'm going to add a 1 to the first section. I'm going to add a 1 to the middle section, which gets rid of the minus 1, and I'm going to add a 1 to the latter section. So now tidying this up, I have minus 3 is less than or equal to 3x, which is less than 9. So this is better than I had originally. I have 3x is bigger than or equal to minus 3, but less than 9. But I want this to be an x in the middle. And how would I do that? Well, I could divide it by 3. And if I divide the middle section by 3, it means I need to divide all of the sections in the inequality by 3. 3x divided by 3 is x, and then at the end I have 9 divided by 3. Minus 3 divided by 3 is minus 1, which is less than or equal to x, which is less than 9 divided by 3 is 3. And you can see that we end up with the same inequality as we found in the first version of doing the sum. Okay, so let's apply the same two methods to this version of the sum in example 10. So here we have fractions. We have minus 1 is less than or equal to a half x minus 2, which is less than 2. Again, I'm going to split the sum up into two parts. The first part is minus 1 is less than or equal to a half x minus 2. And then the second part of the sum is going to be split into a half x minus 2 is less than 2. So tackling the sum on the left, first of all, I'm going to take the number terms on the left hand side. Minus 1 is already on the left, and I'm going to add a 2 to both sides to get rid of the minus 2 on the right hand side. That's less than or equal to a half x. Minus 1 plus 2 is 1, which is less than or equal to a half x. And then to solve for x, I'm going to multiply both sides by 2. So multiplying a half x by 2 gives me x, and then multiplying 1 by 2 gives me 2. So the first part of the solution of my problem is that x is going to be numbers that are bigger than or equal to 2. Taking the inequality on the right hand side now, I have a half x I'm going to keep on the left hand side, and I'm going to put the numbers on the right hand side. So on the right hand side I have a 2, and then I'm going to add a 2 to both sides to get rid of the minus 2 that's on the left. So I end up in the next line with a half x is less than 4. Similarly, if I have a half x and I want to get to an x, I'm going to double it. So I'm going to times it by 2, and if I multiply the left by 2 I get x, and that means I have to multiply the right by 2 as well, and 4 by 2 is 8. And that's the second part of my solution. So x is any number that's bigger than or equal to 2 but less than 8. So we're not asked to list the solution in this question, we're asked to put them on a number line. It's a natural number line, so it starts at 0, and we'll go up 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we've picked a couple of numbers either side of the values in our solution here. A natural number line has full dots representing just positive whole numbers. X is equal to 2, so the first one that I'm going to colour in is 2. And then it's all the numbers bigger than 2 but less than 8. So we're going to colour in 3, 4, 5, 6, 7, and we don't count 8. We can see here in our double inequality that x is not equal to 8, and so we're going to stop at 7. So having a quick look at the second method, we'll write out our inequality again. Minus 1 is less than or equal to a half x minus 2, which is less than 2. I want to get x on its own in the middle section of the sum, and so what I'm going to do is I'm going to add a 2 to each of the sections. So minus 1 plus 2 in the first section to the left of the inequality. Then in the middle section, if I add a 2, that gets rid of the minus 2, and I'm left with a half x. And then on the right hand section to the right of the inequality, I have 2 plus 2. So all I've done is I've added a 2 to each section of the inequality. Minus 1 plus 2 is 1, which is less than or equal to a half x, which is less than 4. And then finally I want an x in the middle, so I'm going to multiply every term by 2. So 1 times 2 is 2, less than or equal to a half x by 2 is 1x, and then which is less than 4 times 2 is 8. And again, we get the same inequality, double inequality, as we got with the first method we used. Okay, so if you want another example of a compound inequality, the trickier example number 6 is an example that you could practice, and despite it not being on the Junior Cert higher level course anymore, and despite its absence on Leaving Cert papers, it is a good question just to practice in terms of looking at double inequalities, which is something that does appear quite often on a Leaving Cert paper, in particular with reference to a quadratic inequality that we'll see going forward. So if you're happy with those questions, move on to the trickier ones, and if you'd like a little bit more practice, just go into the vast bank of questions from the past papers, and you can see lots of examples of inequalities that should help you revise the topic a little bit better. So continuing on with 6 further examples of linear inequalities, I mentioned before that it wasn't a particularly popular question at Leaving Cert higher level, so you're not going to find many examples of true linear inequalities in the papers. One place where I got a sample of a question that might be asked was on one of the probability questions of paper 2. So this is a question about probabilities. We have notation here p hat. Don't worry too much about the notation for now, but just think of p hat as being like another variable, another letter that we have to solve for. So we're given this very simple inequality, p hat minus 0.045 is less than 0.51. So all we want to do with this is we want to collect the p hat terms on one side as we would with collecting x terms on one side. So p hat is going to stay on the left hand side, and on the right hand side we're going to collect the numbers. So we have 0.51 plus 0.045. So we want to get rid of the minus 0.045 from one side, so we add a 0.045 to both sides. And so we get p hat is less than 0.555. And that's it. In terms of the linear inequality, that's the very basic work that's been done. Obviously, there was going to be a difficult aspect to the question in forming this inequality, and that's a skill in itself. But in terms of the actual linear inequality, we can see that we just apply the skills we learnt in the 10 basic examples earlier. So example 2, just another example of where we might have fractions in a linear inequality. So we have 5 minus 3/4 x is less than or equal to 19 over 8. So I'm going to collect the x terms on one side of the inequality and the number terms on the other. So because we have a minus 3/4x, I want to have positive x terms, so I'm going to have the x terms on the right hand side, and the number terms then can be on the left hand side. So 5 is already on the left hand side. To get rid of a plus 19 over 8 on the right hand side, I'm going to subtract 19 over 8. That's less than or equal to get rid of minus 3/4x from the left hand side, I'm going to add a 3/4x on the right hand side. Tidying up the left hand side, I can throw this into the calculator if I like, but what I'm going to do is I'm just going to make 5 an equivalent fraction over 8. So 5 is 40 over 8, and then we have minus 19 over 8, so I'll be able to combine those two terms in a minute, and that's less than or equal to 3/4 x. 40 over 8 minus 19 over 8 is 21 over 8, which is less than or equal to 3/4 x. And then to get x on its own, I need to divide both sides by the number beside the x, which is 3/4. So I have 21 over 8 divided by 3/4, and that's going to be less than or equal to x. So we'll do that fraction work over here on the side of the page. So 21 over 8 divided by 3/4 is the same as saying 21 over 8 multiplied by 4 over 3. Remember, we invert or turn upside down the fraction that's being divided. And we get 21 times 4 is 84. 8 times 3 is 24. And that simplifies to 7 over 2. So going back to our inequality on the left hand side, I have that x is greater than or equal to 7 over 2. Now 7 over 2, remember, is the mixed number 3.5, and it's kind of important to turn it back into a mixed number just when we're putting it on the number line, so we can kind of see easily where things go. We're actually not told what kind of a number line this is, so I'm going to make an assumption and say that this is a real number line just for the sake of argument. So I like to put down whatever the solution is in the middle of my number line. So that's 3.5, so let's have a 3 one side and a 4 the other side, and we'll just add in a couple of numbers either side of those. Now 3.5 is here in the middle between 3 and 4, and we know that x is equal to 7 over 2 or equal to 3.5, so I'm going to actually put a full dot on the number 3.5. It then says that x is every number bigger than this also. So what I'm going to do is I'm going to put in a shaded line to represent all the numbers, including the fractions and the decimals, that are bigger than 3.5. At some stage then I just decide to put an arrow on the end of it to say that it includes every fraction and decimal towards infinity. Question 3 is an interesting question that asks us to find the smallest natural number k such that 2x plus 4 on x plus 3 plus 7 on 2x plus 4 is less than 20 on x plus k. So what's interesting about this question is we have two letters in the question. So we have x's and we have k's, and we're asked to find k. And so the question arises, what happens the x in the question? And we'll see as we multiply out the brackets and simplify each side. So on the left hand side we have 2x plus 4 by x is 4x, 4 by 3 is 12, 7 by 2x is 14x, 7 by 4 is 28. This is less than 20 by x is 20x, and 20 by k is 20k. So if we were to tidy up each of the sides before we decide to collect the terms on one side or the other, what we'll do is let's join the x terms together on the left hand side first of all. So we have 2x plus 4x plus 14x, which is 20x, and then the numbers we have 12 and 28, which is 40. And then on the right hand side I have 20x plus 20k. So what you'll notice is we have a 20x on both sides. So if we subtract 20x from both sides, that actually cancels out all of the x's, and the x's are gone from the question. So we're left with, on the left hand side we have the number 40 is less than 20k. We're looking to find k, so I'm going to divide both sides by the number beside k, which is 20. So 40 over 20 is less than 20k divided by 20 is k, and so k is greater than 2. Now, when this question was asked a couple of years ago, a lot of people left this as the answer. So it's important always to go back and read over the question again. So the question says, find the smallest natural number k such that this statement is true. So k is bigger than 2. Well, what's the smallest natural number bigger than 2? Well, 3. So 3 is the actual answer to this question. So 3 is the smallest number k could be. K could be. Yeah. Okay, so really important just to read the question over again. So question 4, we're asked to find solutions for two separate linear inequalities, and then the third part of the question asks us to find the intersection of these two sets. So taking the first inequality, initially what we have is we have 3x minus 2 is less than or equal to 4. So keeping the x's on the left, we have 3x, and bringing the numbers to the right hand side, we have 4 plus 2. So 3x is less than or equal to 6. Dividing both sides by 3, we get x is less than or equal to 2. What you'll notice is that I'm taking more shortcuts than I would have done originally. So it's easy to see. Moving on to question 2, we have a fraction. So we have 1 minus 3x over 2 is less than 5. And when we have a question with fractions like this, the handiest thing sometimes to do is to multiply all the terms on the left and all the terms on the right by whatever the denominator is of our fraction. So if I multiply the left hand side of this inequality and the right hand side of this inequality by 2, it will get rid of the fraction from the left hand side. 1 minus 3x over 2 times 2 is just 1 minus 3x. And then if I do 5 times 2, I get 10. Now, we've also mentioned that a shortcut that some people like to take is the number on the bottom of a fraction one side gets multiplied up by the term on the far side. So it is only a shortcut, and it is better to think of yourself as multiplying both sides by 2, but some people like to use that little trick to get to the next step. This time we'll collect the x terms on the right hand side and the numbers on the left hand side. So we have 1 minus 10 on the left hand side and we have plus 3x on the right hand side. 1 minus 10 is minus 9, which is less than 3x, and then dividing both sides by 3, I get that x is greater than minus 3. So in finding what A intersection B is, A is the set of elements that are less than or equal to 2. All of the integers, all the positive and negative whole numbers less than or equal to 2. B is the set of integers, all the positive and negative whole numbers that are greater than minus 3. And we're looking for which of the numbers satisfy both of those sets or are included in both of those sets. So we're looking for elements that are in common in set A and set B. And so starting with numbers that are bigger than minus 3, integers bigger than minus 3, minus 2 is the first integer bigger than minus 3, then we have minus 1, then we have 0, then we have 1, and we would continue to go if there was no other condition on the question. But the other condition is it also has to be in set A, which says that it has to be a number less than or equal to 2. So we'll go as far as the number 2, it's equal to 2, and then we'll stop. And those 5 elements are in both set A and set B. They're greater than minus 3, but they're less than or equal to 2. So example 5 is a functions question, and I've included it here just because the bottom line includes a linear inequality. So we'll run through the whole question. It's a topic that you may not have revised for some time, so functions is something that you may not have seen for a while. But if you stick with the question, there's good revision in functions, and then we can see how a linear inequality can be applied to a question like this. So let's first write down each of the two functions that were given. So h of x is equal to 2x minus a. So that's our first function. And then we're told that h of 3 is equal to 1. h of 3 is equal to 1. So let's get that down. h of 3 equals to 1. What that means is if I substitute an input of 3 into the function for x, then the output of the function is 1. So if I sub 3 in for x, so 2 by 3 minus a, so I've taken the function and subbed in 3, then that will be equal to the number 1. Tidying this up, 2 by 3 is 6, minus a equals 1. We're solving a linear equation here, so 6 minus 1 equals a, and so 5 equals a. And so with this first piece of information, h of 3 is equal to 1, we were able to work out that a has a value of 5. And what I'm going to do is I'm going to actually update my function down the bottom of the page here just to reflect the fact that I now know that a is equal to 5. So h of x is equal to 2x minus 5. Now I'm going to do the very same thing with our second function. So our second function is k of x is equal to ax plus b. Now remember, we've just found out that a is 5, and so I'm going to update that and say that k of x is the function 5x plus b. And I'm going to go and try and find out what b is using the other piece of information that they've given me in the question, that the k of 5 equals 8. So if I write down k of 5 equals 8, what does this mean? It means that if I put 5 in for x into the function as an input, the output of the function is 8. So let's go ahead and do that. So we have 5 on 5, I'm subbing 5 in for the x, plus b equals 8. 5 times 5 is 25, so 25 plus b equals 8. And then bringing the 25 over the other side and subtracting, I get b is equal to 8 minus 25, so b is equal to minus 17. Now, the fact that I have it as minus 17, what I'm going to do is I'm going to go and update my function k of x. K of x is now the function 5x plus b, which means 5x minus 17. So the first part of the question is a purely functions question where we're given information about inputs and outputs, and we can use that to find the values of a and b. It's the third part of the question that we're interested in, which asks us, or tells us rather, that h of x is greater than or equal to k of x, and to find the values of x for which this would be true. So remember, h of x is a function that we have simplified as 2x minus 5. So down here we were able to work out that h of x was 2x minus 5, and that's greater than or equal to k of x, which we worked out was 5x minus 17. So 5x minus 17. And now finally we have our linear inequalities part of the question. So this is a simple linear inequalities question. We're going to collect the x terms on one side and the number terms on the other. I'm going to collect the x terms on the right hand side because I know that when I simplify them, the x term will be positive over there if I do that, and the numbers on the left hand side. So on the left hand side I have minus 5, and then to get rid of minus 17 from the right hand side I'm going to add a 17. On the right hand side I have 5x, and to get rid of 2x from the left hand side I'm going to subtract a 2x from both sides. Simplifying both sides, I have that minus 5 plus 17 is 12, and 5x minus 2x is 3x. To isolate the x or get the x by itself, I'm going to divide both sides by the number next to the x, which is 3. So 3x divided by 3 is 1x, and 12 divided by 3 is 4. And so the solution to this inequality is x less than or equal to 4. Now the question says to list those values, and it tells us that they're natural numbers. So I'm going to list all the values, all the natural numbers, the positive whole numbers that are less than or equal to 4. So 1, 2, 3 and 4 itself. So a reasonably straightforward question from the linear inequalities point of view, though some people might have had some difficulty in actually getting to that stage in the first place. So the final example is another compound inequality, and as mentioned before, this has been removed from the Junior Cert higher level course, so we're kind of practicing here for demonstration purposes only, and just to further explore the idea of double inequalities, which still do appear on the Leaving Cert higher level course. So in taking this question, what I'm going to do first of all is write it down in full. So I have minus 17 is less than or equal to 1 minus 3x, which is less than 13. So first thing I'm going to take minus 17 is less than or equal to 1 minus 3x, and I'm going to make a linear inequality out of that portion of the sum, and then I'm going to form my second linear inequality from 1 minus 3x is less than 13. So solving each of these linear inequalities, the first thing to note is that there's a minus 3x on the right hand side of my first inequality. I'd like that to be a positive 3x, and so I'm going to collect the x terms on the left hand side. So to get rid of a minus 3x from the right hand side, I'm going to add a 3x to both sides. To get rid of the minus 17 from the left hand side, I'm going to add a 17 to both sides. So I'm left with 3x is less than or equal to 1 plus 17. 3x is less than or equal to 18, and x is less than or equal to 6. Taking the inequality on the right, this time I'm going to collect the x terms on the right hand side. So on the left hand side I'm going to have the numbers. 1 is already on the left hand side. To get rid of a 13 from the right hand side, I'm going to subtract 13 from both sides. 1 minus 13 is less than. To get rid of minus 3x from the left hand side, I'm going to add a 3x to both sides. 1 minus 13 is minus 12, which is less than 3x. And then finally, dividing both sides by 3, I get x is greater than minus 12 divided by 3 is minus 4. What I can do now is I can join these two portions of the sum. So what I can say is that minus 4 is less than x, which is less than or equal to 6. So the solution set of this question is all the numbers that are bigger than minus 4 but less than or equal to 6. We're only interested in integers, so positive and negative whole numbers. And so we'll just pop up our number line here. So you can see our number line consists of full dots on all the positive and negative whole numbers that are bigger than minus 4, so starting at minus 3, all the way up to and including the 6. 6 is included because our inequality has less than or equal to 6. So in truth, the trickier example is probably not that much more difficult than the key 10 examples that we would have done originally. But again, the reason for this is that the linear inequalities play a limited part of Leaving Cert's higher level questions in general. So that's not to suggest that we might not get a more difficult linear inequalities question in the future, just that they haven't been asked thus far. So that wraps up session 2 that's taking a look at linear equations and linear inequalities, and we're moving on to the next session, which is going to take a look at factorizing expressions.